This is chapter 4, number 56. It's a double Atwood machine. An Atwood machine is just anything that has two that has boxes over a pulley. So I'll just start by talking about the concept on how to solve a problem like this. First, if you want to find the acceleration of all the masses, um, start by doing the top one first. Treat the bottom part of the Atwood machine like a combination. I mean, like it's just one mass. Fortunately, they said the pulleys and the ropes, the cables, are massless and frictionless. So that helps us out a lot. So we can just treat this second part of the Atwood machine as just one big mass and figure out what the acceleration is of that first. Once we know that, then we can find the acceleration of just the bottom part. And once we get both accelerations, the acceleration of the top part and the bottom part, for the bottom part we can add the first acceleration, so we get the total acceleration of the thing. See how much it's falling faster and faster downward. Okay, once we get that, then we play with the tensions. We use our formulas for finding the total sum of the forces. The tension in over here. The tension at the bottom part, however, will depend on how fast it's moving downward. Will depend on the tension on the first part. So we will need to take that into account. Okay, let us begin. So here's the first part where the whole thing is treated as one, and here's mass C. Here are free body diagrams. Here's the force of gravity acting on A and B, and here is the tension pulling back up on it. Here's the second box, is mass C, force of gravity acting on C and the tension pulling up on it. This arrow is the direction of the acceleration. Notice that MA plus MB is probably heavier, so I'm going to say that it's accelerating in the direction of MA plus MB. And it's going counterclockwise. So I'm calling the counterclockwise motion positive from negative from the other side. Okay. Now we can do the sum of the forces. For A plus B, okay, the sum of the forces in the y direction equals the force of gravity of A plus B minus the tension equals, here it's moving, so we'd say MA plus MB A. So total mass times the acceleration. Okay. Now for C, or mass C, we look at the sum of the forces in the y direction. The positive force is the tension in this case, because the object is moving upwards. So tension minus the force of gravity for box C equals MC hammer. No, MC times acceleration. Okay, let's up. The tension cancel that out. We got FG A plus B minus FD of C equals A plus MB plus MC A. Now that we have that, we can replace this with the knowns. Believe it or not, I wrote down MA equals MA, MB equals MB, MC equals MC because it's like we know them. That they gave them to us, even though it's in letter form. Those are the knowns. So write this out. MA plus MB, mass of box B, times G, minus mass of box C, G, equals this whole thing. Well, I'm going to divide both sides by MA plus MB plus MC. Let's put that on the bottom. Okay. Now we can actually go a step further and the G. Okay. So let's factor out the G. And we get MA plus MB minus MC all over MA plus MB, some of the mass of all the mass, and that's very common. You have to take into account the entire mass, so it's usually a fraction of the entire mass that the acceleration is. Okay, and that is the acceleration of the mass of C. More to come.